Okay, welcome back everyone. Ahead of tomorrow's briefings, we're now going to dabble in a little bit of artificial intelligence. I'm currently sharing the stage with Jonathan Armstrong, who's going to talk to us about the AI revolution in healthcare. Jonathan is a machine learning engineer at Cerdan, and he is now going to give us his body of work. I'm just going to leave the stage with you.
Excellent. Thank you very much, Peter. Well, it's a privilege to be here, and I'd like to thank Peter and the organisers for the opportunity. And I know we've been having a very tech-centric conference so far, but I think it's interesting just to see how some of these very new and innovative technologies are really being applied in the real world. And it's hard to get anything more real than healthcare at the minute. And especially with all of these COVID pressures in healthcare, I think it's important to show where AI is really making a difference in the real world. So a little bit about myself. My name's Jonathan Armstrong. As Peter already said, I'm a machine learning engineer at Cerdan. I'm also doing a computer science PhD at Queen's. And my background is in mechanical engineering. I have a degree from Brazil in mechanical engineering. You might be wondering why I have that picture there in the background of the slide. That's because that's a power plant where really my AI journey started. And I applied AI to that power plant for my final dissertation project. And then when the opportunity appeared here in Cerdan in Lisbon, I came over to start applying AI, the same technology and principles, applying that to medical imaging. So let's quick overview of what we'll be seeing this morning. Just looking first at the challenge in healthcare at the moment, the possibilities that there are, what the current tech, what the current research has been doing in AI and healthcare. Where do I fit in this whole scheme of things? And the key takeaways for today. So when we look at the challenge in healthcare, well, it's hard really to know where to start. There's a bunch of different challenges. The main challenge at the minute, obviously, is the COVID-19 crisis. And that has been putting great pressure on the healthcare. There's also a growing population that's a crisis or a challenge. An aging population is also a challenge because you start running into a bunch of different diseases and illnesses. There's a great funding crisis in the NHS. The budget at the minute is somewhere around 20.6 billion, and when they did a research into it, the budget should be around 50 billion, so that's a challenge. And also one of the big challenges, which I think is relevant to Beltech, is the digitization. And when we talk about digitization, that really means, some hospitals are running in Windows XP, and you now have to transition them over to more new and innovative technologies. And so that's estimated to cost maybe around 13 billion. To the NHS to just do that digitization and that transition. But talking about the challenges, I would like to focus a wee bit more in my area, which is medical imaging. And when we talk about medical imaging, if you start looking at the number of images taken per month over the last 10 years, there has been an increase in the number of diagnostic images by about 5.6%. And to a certain extent, you might say, well, that's a really good story. That's excellent to see that. But the big difficulty is that the waiting list for those exact images has been increasing at 8.6%. So they're not even supplying the current demand. They're falling short, and thus the waiting list, they're fighting a losing battle because the waiting list is increasing more than the actual images. And around medical imaging, our focus has been mainly in the radiology and the pathology side of things. Pathology is a totally different and new technology coming into digital pathology. That's why I mentioned the digitization. But radiology and pathology are the two big areas that we're looking at, mainly because those are the areas where a lot of the clinicians are put under a lot of pressure because of the screening programs that are ongoing in the UK at the moment and here in Northern Ireland. Those screening programs put that additional pressure on those clinicians that they now have to do that beyond their current work. So just looking directly at radiology, it is estimated that only 1 in 5 UK trusts run a safe 24-hour radiologist service, 24/7. And that costs the NHS around 165 million a year in outsourcing and sending those even to Australia, for example, to do those additional tests and to get eyeballs on those scans. When we move to the digital pathology side of things, or the pathology labs, sorry, digital pathology is a new advance, only 3% of NHS pathology departments have enough staff to meet the clinical demand. Only 3%. And so that they estimate that costs the NHS around 27 million in that same outsourcing and in that same passing those tests off to other places so that the waiting lists don't get any bigger than they currently are. So that just gives you a small snippet of the crisis and the challenge that there is in healthcare, mainly focusing on the medical imaging side. But then it's a question, well, what are the AI possibilities for this? What is being currently done in the medtech space, in the medical technology space, to deal with these problems? Well, the possibilities are many, but they all center around one thing, and that's patient data. And when we start looking and analyzing patient data, that's where AI really comes into play. It can analyze massive amounts of data in a short space of time. It doesn't ask for a salary rise. It can do it 24/7 with the same focus and intensity. And starting off, even in the COVID crisis, AI has been used to, even from surveillance point of view, AI algorithms detected COVID before the World Health Organization. It's being used to discover new drugs, or maybe rediscover old drugs that could be applicable for COVID-19. And as well, it is being used to predict drug responses by analyzing someone's genome sequence and see how they will react to that drug. It's also being used in a very interesting way with regards to hospital infections. In the University of Michigan, researchers developed an algorithm that is able to predict hospital infections maybe 5 days sooner than was normally seen. So very quickly you can start to incisively deal with those problems. It's able to predict no-shows with even up to 90% accuracy. In the University College Hospital in London, they were able to predict that people wouldn't show up for an appointment. So you might say, well, that person is we're virtually certain that person isn't going to appear because of our algorithm, and now we just add somebody else into the waiting list, and very quickly you reduce the waiting list just in that very simple way. Scarily, it can predict Alzheimer's disease based on just a snippet of someone's voice. That's with 82 to even 100% accuracy. It can predict Alzheimer's just by someone saying a phrase into an audio and turning that in and looking at it with AI. It's being used in wearable technologies. There's a current pilot in southeast England that more than 500,000 people, their vital signs are being monitored gradually just to see how they're getting on, let's say post-surgery or something like that. And the number of intensive care stays and the number of reintroductions into hospital have reduced drastically. And then we come back to the medical imaging side of things and radiology and pathology, and that's really what I want to spend the rest of my talk on. So, where do I fit into all of this? Well, I came over here to Northern Ireland for the KTP program. That is a knowledge transfer partnership where you transfer knowledge into a private company. And so I'm working with Queen's University Belfast and Cerdan in Lisburn to start introducing AI into the company. Cerdan, a little bit of background about the company. They're a LIMS provider, Laboratory Information Management System provider. So they provide the software for pathology labs mainly and hospitals. They also work in the medical imaging side of things, then looking at x-rays mainly around breast tissue and then looking at pathology as well. And so we've come back to these two big themes, radiology and pathology, more specifically in my case, mammograms and colon polyps. The issue is that they're two very different beasts. Radiology has been going on for many years, mainly because of what you see here. Every image can be around 1 megabyte. So that is a lot in comparison to normal text. The old saying is, a picture is worth 1,000 words. That's fair enough. But then when we start looking at pathology, every image can be up to 10 gigabytes in size, which is massive in comparison. And that's where the limiting factor starts to come in. And that's why digital pathology is only becoming a thing now, and then AI is the driver for digital pathology, in my opinion. But looking first at mammograms. Well, I'm using an open data set because of my research, just using it with Queen's. It's called the MIAS data set. There are 322 mammogram images. Here's one, you can see it here. That's really a depiction of everything there. And also in that data set, then there's what we call ground truth, which is the background information for every image, basically the clinical diagnosis for image. And then you can train your algorithm saying, here's the picture, here's the diagnosis. And that's how you train your algorithm. So then, just give you a quick walkthrough of how we train the algorithm. Well, first of all, you start out with the image. Here in the red circle is just a visualization of that ground truth I mentioned there a slide ago. And then we divide the image into little patches, because that's easier for the algorithm to learn. The algorithm doesn't have to be as big, but can learn faster. and you have more information because, as I mentioned before, we only had 322 images, which isn't that much. But when you divide the image into patches, that every patch outside that red circle is actually a negative patch, and every patch inside the red circle is a positive patch, unless you tell it positive or negative, and you train your algorithm like that. The algorithm looks something like this, and I know that might be Greek to people who aren't in AI, but we use a VGG-style architecture, training it with around 8,000 negative patches and 8,000 positive patches, so you need a balanced data set. Doing what's called five-fold validation, so that you always have to train your algorithm and test it on something else. So this testing happens across the algorithm 5 different times, so that you ensure that you're not getting a biased result or a bad result just because you were lucky and got easy to diagnose little patches. And so I've reached around 92% accuracy so far, but then training is ongoing in this research. But you might be asking, well, just algorithms, what's interesting about all of that? Well, that's where the wow moment comes in. And this really happened to me a wee while ago, but when I did a classification on each one of these mammograms, just a sliding window, instead of dividing it into patches, just checked each little patch to see if it was positive or negative. And you do a heat map of where it thinks there might be issues. And then that's what came out there on your right. That's what the algorithm detected. And you can start to see those points. If you remember back to the previous couple of slides, the ground truth indicated that spot down in the bottom right. And so the algorithm, just through a simple sliding window, was now starting to be able to diagnose and point out where the issue might be. And this could be essential to somebody with less training, just to guide their eye and show them where the issue might be. The issue, the patch on the top right, on the top left, sorry, I believe is just a shadow it's diagnosed. And that could be, maybe recheck this point because there might be an issue, but there isn't as much, so you can move on with the diagnosis. So that's really, from the mammogram side of things, how the research progresses. But you might be asking, well, what about pathology? What about the colon cancer side of things? Well, in colon cancer, and I'm not a pathologist, so I apologize, but the progression tends to be, it's like a little skin tag that just grows inside your colon. And that progresses, and it could take 10 years for that to become cancerous. So for the first period, it's called an adenomatous polyp. That is before it turns into cancer. But once it turns into cancer, then it's very dangerous. The solution to that is what we call the bowel cancer screening programs that have been ongoing. Maybe some people have participated in it. But the bowel cancer screening program then involves a person taking a colonoscopy. And here we have at the top right of the image a digital image of a colonoscopy. I didn't want to traumatize everybody and show a real image. But we've got the digital colonoscopy up here, and that's really what happens. The colonoscopy happens, those little polyps are extracted. Once they're extracted and harvested, they can't do the person any harm anymore. But they have to be tested and checked to see how advanced the cancer is, or how advanced they were along that graph that I showed before. And so when you check them, you start slicing them into little pieces and look at them under a microscope, and that's the job of a pathologist. When he looks under a microscope, this is really the little appendage we mentioned before. This is the wee thing that has been extracted, that has been taken out of someone's colon. And so when you start looking at it, you can see a denser part. That is the part that is becoming adenomatous. And that's called tubular adenoma. That's the technical name for it. But really where AI comes in is where it's being put pressure on the pathologist and where they're doing the mundane tasks. So they're starting to count maybe the number of cells in that area. Maybe they're counting the distance between these 2 points to know the extent of it, the area, the size. Those are things that would be very easy for an algorithm, but it takes pathologists time. And so that's really our goal in all of this, is going to the key takeaways now, that AI can revolutionize healthcare by doing the mundane, by doing that objective analysis, by taking away those little things that take a lot of the researchers or pathologists' time. And so you maximize the use of clinical time. You maximize them looking at the difficult cases, looking at the most important stuff, and thus you enrich the decision making. You make medicine faster and better by enriching the content that they see. But that's only possible if you integrate it seamlessly with their workflow. It can't be that they take time out of their day to go and click something else. No, it has to be integrated seamlessly right through their workflow, supplying that extra information. Let's say supplying that little image that I showed you before of where the heat map of the problem would be. And really the key guider to me in all of this has been a quote that I really appreciate by Jenny Romity. She's the CEO of IBM. And she says that it is vital to make anything about AI explainable, fair, secure, and with lineage. Meaning that anyone could very simply see how any application of AI is developed and why. And that sums it up. You need to be able to show, as a researcher in this field, how it started out, where the images came from, that there's no bias and so on, right through to the diagnostic aid that you're supplying the clinician at that time. And that's really it. So thank you all for listening. I hope that gives you a bit of more of an insight of where AI is really being applied in the real world, the opportunities and the possibilities around that. And I look forward to you getting in contact with any questions. So thank you very much, Peter.
Jonathan, thank you very much. That was fascinating. I really, really enjoyed that. So, thank you.